Okay, we want to show that multiplying elements with 0 gives always 0. So for this purpose, we just take some element of our field K. So since, by definition, 0 is the neutral element of addition of plus, we know that if we write down x times 0, so 0 is neutral with respect to addition, so 0 is the same as 0 plus 0. This doesn't change anything. So this is x times 0 plus 0. But now we know that this is a field, so we have the distributivity property, which means this is field property K3. Having a field day today. So this, by distributivity, just means this is x times 0 plus x times 0. We've shown that x times 0 is x times 0 plus x times 0. So what we can now do is just to add minus x times 0 on both sides. Which yields that x times 0, on this side, if we add the inverse of this will just become 0. And on the right-hand side, we get x times 0 plus x times 0, and then we've added minus x times 0. And here we again know that this parenthesis, this is associative, so we can again shift the parenthesis, get that this is x times 0 plus x times 0 minus x times 0, and this is by definition 0. So this becomes x times 0. So we've shown x times 0 equals 0, what we wanted to do. This might look a bit pointless, but this is really using only formal properties and then confirming that all the rules that we have already follow from these axioms, and that we really don't need any more than that. Yeah, this is the way we've shown this property. Now we come to another property. Again, something which looks reasonable to do, but really need to keep notice of this because we will use this in computations. If we have an arbitrary field, then for all elements A, B from the field K, we have two nice properties, namely minus A, the additive inverse of A, times B is the same as minus of the product A times B. And second part, if we multiply minus A times minus B, so two additive inverses, we see that again in fields we just get A times B. So this rule that minus times minus is plus, this holds true in arbitrary fields, which is really beautiful. Okay, and the proof of this thing I will leave up to you, namely this will be an exercise on exercise sheets 0 or 1, I haven't decided yet, but this will be on one of the exercise sheets that you get. This is again, you just need field axioms, this is not too hard, this is just following the simple approaches as the rules I did before. Okay, another property that seems quite natural but that we need to show. Again, that K plus dot be a field. And we take two fixed elements, A and B and K. If the product of A and B is 0, then then A is 0 or B is 0. So a product is 0 if and only if one of its factors is 0. We know, like, we have already seen that if one of the factors is 0, the product is 0. That was the theorem that I proved just up here. But the other direction also holds. So this is something that is really quite elementary for arithmetic, and that we will that this holds here in general for fields. Proof. It's not only that we're confirming this for real numbers. We will a little later we will introduce the complex numbers, which is another example of a field, and we will get then that all these rules hold in the complex numbers. We get this for free because we've already proven this for general fields, which is a nice thing. Assume that A times B is equal to 0, but A is not equal to 0. Then we know if it's not in 0, so it's part of K star, so it has an inverse. So we know that A minus 1 in K is well defined. Then we get the following computation. We know that A minus 1 times 0 is equal to 0. So this is using the theorem, what was the number? 132. So this holds, but we've assumed that A times B is 0, so we can replace this by A times B. So A minus 1 times A times B, and then we can again use associativity here. So we need that K star with respect to multiplication is an abelian group. So this is using property K2. This is the same as I minus 1 times A minus 1 times A times B. This is the neutral element, so multiplying with this doesn't matter. So this just gives B. So we have shown B is equal to 0. So if one of the factors is not 0, then the other one is 0, and this shows the claim. Okay, so this for basic arithmetics in fields. Now we want to add some extra structure, because the real numbers have some other structure that we haven't used until up to this point, namely they are ordered. If we have two numbers, we can always say that one is bigger or smaller than the other one, or we can compare these numbers. Any two numbers can be compared, and we can say that they are equal, lower, bigger than, smaller than, and so this is what we can do there. And this is an ordering. And this is the next thing we want to formalize. We want to define orderings on fields that have nice properties, and this will make another big step towards the real numbers. So how do we define such an ordering abstractly? I mean, of course, we all intuitively know how to compute with these things, but or how these things are defined, but how can we define this on arbitrary sets? So we start very elementary. We start with a set M. In case you're wondering why sets are mostly called M in this lecture, in most math lectures here, at least in Germany, because set in German means Menge, which starts with an M. So this is kind of the way that M is popping up here all the time. Okay, let M be a set. A binary relation on M is something that sounds more complicated than it is. This is nothing but a subset, which we call R, as a subset of M times M, the Cartesian product of M with itself. So what does this have to do? Maybe you see it if I write this a bit clearer. We write X, R, Y, a bit awkward notation, but we will see in a moment why this makes sense. We write this if and only if X, Y lies in R. So imagine we replace now the letter R by the number, rule smaller than, which we know from the numbers, and assume we replace M by the natural numbers, the integers or rationals, for example. Then we can here say that X is smaller than Y if and only if the pair X, Y in R. So R would then consist of all the pairs for which the first entry is smaller than the second one. And this is the way how you can really formalize these relations, so these orderings. Namely, ordering is a special kind of binary relation, and this is part B of the definition. A total order on M. There is also a notion of a partial order, but I will skip this one because we won't need it. A total order on M is a binary relation, and this we will denote by smaller than or equal to, so using this familiar symbol. On M, which has some nice properties. And now we can really see that we can again abstractify the usual properties of this symbol that we associate with it when we consider the numbers that we know from high school. So first of all, X is smaller than or equal to X. This is what we want to have. This makes sense. I mean, this is something that's obviously holds true for the relation we know. So for all X in the set M, and this property is called reflexivity. The names here are not that important. I will just drop them so in case some textbooks or something are using them, so you know what this means. So it's more of, pay more attention on the math here than on the names. That's important. Okay, then another nice property, fx is smaller than or equal to y, and y is smaller than or equal to x. So if both of these things hold, then it should follow that x is equal to y. This is the second axiom we demand. This is called anti-symmetry. Okay, third thing is another thing which is kind of obvious for the known relations. If we know that f, x, y, z in M satisfy, sorry, maybe, no, sorry, keep it a bit simpler. If we have three numbers, three elements of M, sorry, this here holds for all x, y, and M. And here we want for all x, y, z in M, so we take three elements. If x is smaller than or equal to y, and y is smaller than or equal to z, then we want, and you can now guess what I want, x is smaller than or equal to z. So this transfers here, and this property is called transitivity. Okay, and a fourth thing. So if I have two elements of M, I want to be able to always compare them, which means it should hold that x is smaller than or equal to y, or y is smaller than or equal to x. But I'm always able to say something about them, because in general, if I would miss this property here, so this is called totality. If I would miss this property, there's no reason why any pair of elements could be comparable by this relation. They wouldn't be, there could be two elements which I just couldn't tell if they are smaller than or equal to or not. So this doesn't, where not one of these two, they might not be related at all. So that's the point here. Okay, yeah, I'm writing too big, I already need to erase. Now, as the next step, we want to equip fields with orderings, and not only just orderings or total orders as in the sense we did before, but we want these total orders to behave nicely, in some sense, or reasonably, with respect to the addition and the multiplication of a field. And this we will now formalize what this means. Definition 136, a field K plus dot is called ordered if it admits a total order, which we again call smaller than or equal to, such that the following properties hold. I call these ordering axioms O1, so this is an O, not a 0. O1, if x, y, and k are chosen such that x is smaller than or equal to y, and we take a third element z in k, then we want that addition of this element doesn't change the relation, which means then x plus z should be smaller than or equal to y plus z. This makes sense. We're kind of adding something is just kind of shifting the addition. Yeah, second ordering axiom. If x, y, z in k satisfy, again, x smaller than or equal to y, and now we assume that 0 is smaller than or equal to z. So 0, again, as abstractly as the neutral element of addition, and so we want something that's in this relation, so which you would call in real numbers something non-negative number. I will formalize this in a second. So if this holds, then we want that multiplication with z doesn't change the order. which means x times z should be smaller than y times z in this situation. Oh, the camera just made a funny sound. I just have to check if the... All clear? Okay, sorry about that. So this is what we want. So operations, addition and multiplication should behave, or the order should behave reasonably with respect to these operations. So we can really do computations with inequalities. This is what we really want to do with it in this sense. So and now just some notation, and again just transfer some notation from real numbers, which we already know from school, to make things a bit easier. Namely, if k is, let k be an ordered field, we call an element x in k. Non-negative if 0 is smaller than or equal to x, positive if it's non-negative and it is non-zero. And now the same thing in the other direction. We can also say non-positive if x is smaller than or equal to 0, and finally negative if x is smaller than or equal to 0 and x is not equal to 0. So this is a nice thing, because if we have some abstract field with an ordering, no matter how it's given, we always have this notion of positive and negative, and we can really generalize all the formalism that we so deeply love from high school. Okay, so much for that, and some notation for all x, y, and k. We then define the following. First of all, we say that x is smaller than y, so we just introduce the standard notation, if and only if x is smaller than or equal to y and x is not equal to y. And keep in mind, this operation hasn't been defined yet. We just have this formal thing smaller than or equal to, and these two things already were defined in our notions, and so I use them to define the additional notation here. Then we want that x is bigger than or equal to y, if and only if y is smaller than or equal to x. Okay. And finally, x should be bigger than y, if and only if x is bigger than or equal to y, and x is not equal to y. So very formal, very technical, but now we have transferred many notions that we know from the real numbers to some abstract ordered fields. Okay, just an example. First of all, the natural numbers, they have an obvious ordering. You have just 1, 2, 3, so this is something we just intuitively used. So consider n with its, I write this in quotation marks, obvious total order. Then we can take the field Q. We will define the natural numbers formally in a bit. If we now take the rational numbers Q, we have seen that Q plus dot gives a field, and that now we can also see this is an ordered field. Sorry, not, don't want n, sorry, I want z, the integers. They are, of course, also, we have this notion of the standard total order, sorry about that. So they are ordered nicely. And we can see that the rational numbers, which are also now quite formally defined, they are an ordered field as well. Ordered field with respect to the relation smaller than or equal to, given by the following. So A over B should be smaller than or equal to C over D. And we can reduce this or trace this back to the case of the integers by just multiplying with the denominators. So we know that denominators are natural numbers as the way I've defined Q, so multiplying with them won't change the order. So, but this is, we define it, that this should hold if and only if A times D is smaller than or equal to B times C. So simply by multiplying both sides with B times D. And this is basically what we want. And this is now an integer, this is an integer, so we can use the order from before and get an ordering of the rational numbers. Okay, so I won't check that this is indeed the total order that satisfies these axioms, and this is something that's a nice exercise for you if you are interested in kind of seeing how these orders work. So I recommend to check this if you want to feel more familiar with. So this should hold in Z. Okay, just some notation before I go on. For any number n in N and x in K in a field, I just introduced some standard notation, namely n times x, or n simply nx. This is what we write the n-fold addition. So we add x to itself n times. Right? This is the same thing we do in real numbers, and we want minus nx to be minus x, minus x, minus x, minus x, and again add, so we add n copies of minus x. So this, another way of writing this would be then n times minus x, and then defining this as in the line before. The same thing with multiplication. We define x to the n, so we introduce exponents here at this point. So this is then defined like this is defined like this, and x to the n is defined by x times, and so on, times x, using the multiplication of the field. So this again, n times. And x to the minus n, we can define this simply by the inverse x to the minus 1 to the power of n. So with respect to this, which means that explicitly this is x minus 1 times x to the minus 1 times and so on. Okay, oh, and finally, sorry, can maybe add this here, x to the 0, so 0, the neutral element of addition, sorry, no, nonsense. 0 as the exponent here should just formally be defined as 1, as the neutral element of multiplication. So, yeah, this is standard notation that we will use for fields where we have additional multiplication from now on, and this is something that you shouldn't have any problems with, but this is just something we need to technically define. Okay, for the next blackboard I'm cheating. Okay, I've cheated a bit. I've prepared this theorem because this theorem collects basic facts about ordered fields, because we have seen that several arithmetic rules for fields hold just assuming these axioms, and in the same thing we can then derive many inequalities that are really pretty standard from the ordering axioms. And I think there's no big point in discussing this here. I've put this completely into the, so the complete version of this theorem is in the lecture notes. I won't prove this at this point here because it's something that's, again, derived from the axiom, and it would take a very long time to prove all these relations. And it's not really all that interesting. But I encourage you, if you are really interested in these ordering things, try to prove them yourself. All that's needed are the axioms of an ordered field. And just I discussed these few examples. Namely, we have an ordered field. So first thing is we know that by the ordering axiom 01, here it is, we know that orderings here are preserved under addition of elements of the field. And here is the same with strict orderings, so, or with strict relations here. Namely, if we have A really strictly smaller than B, then A plus C is also strictly smaller than B plus C, which we know for the real numbers is to be true, but this, yeah, we need to prove this for the axioms, from the axioms here again in this setting. And also, if we have a positive element, then the product of A and C is smaller than the product of B and C. This is kind of, yeah, more derived. So we have O2, the second ordering axiom. We only know that this relation smaller than or equal to is preserved by no negative numbers, but if we have these strict inequalities, we don't know yet. So this is something we need to show. And here also, if we have, this is kind of from the transitivity of a total ordering, we know that if A is smaller than or equal to B and B was smaller than or equal to C, then A is smaller than or equal to C. But here, if we know that the second one is strict, then we get that this is strict as well. The same would hold if the first one is strict, which I won't prove at this point here. and so on and so on. So with C, we have the same relation that if we have two inequalities here, and at the two left-hand sides, it will be smaller than or equal to the sum of the two right-hand sides. And the same thing if one of them is a strict inequality here, then the result will also be a strict inequality there. This is all pretty obvious, but technically you need to show. So parts D and E I haven't written here as I haven't with G and H. I just want to mention property F here because this is something I find quite interesting and we will also need this later. The square of an element is always non-negative. This is what we know for real numbers, but indeed this holds for ordered fields already. And if the element is non-zero, then the square is positive, so it's non-vanishing as well. So this is some very important thing, and this is some, you see that most fundamental properties of the inequalities with real numbers already hold here for ordered fields in general. Okay, now I need to wipe. Now that we have notions of positive, negative numbers available and non-negative, non-positive, we can generalize another nice construction from the real numbers to arbitrary ordered fields, namely the absolute value of a number. And this is something that you also probably intuitively know, but if I would ask you to write down a formal definition of the absolute value, you would maybe think, and there are some ways of doing so. And I can now use the definition which works in arbitrary ordered fields. So we have an arbitrary ordered field, we have an element of this ordered field, x, then the absolute value of x is the following number. So we denote this by these vertical lines, as you know. Or as you did for real numbers. So if the number is non-negative, we just leave it as it is. So it's just x, and I'm using this big brace here to use a case-wise definition. I haven't used this before, but I think you should be familiar with that. This is what, if we define this in several different cases, we list the cases one by one and put a big opening brace in front of it. Okay, we leave it as x if x is non-negative. So if it's negative, what do? We make it positive. This is the idea. So we change its sign, and this is something that we can do quite easily. We just define it as minus x if it's a negative number. If x is smaller than 0. And this definition doesn't use any special thing of the real numbers, we just have used ordered fields. So, now we take a look at properties of this absolute value. Okay, let K be an ordered field. Then, for all elements x and y of K, we have the following properties. First of all, the absolute value of a number is always non-negative. This is very easy to see. I mean, this follows right from the definition. This is something also from the ordering axioms that I have in this theorem where I have this, they're just erased with all the ordering properties. We can see that minus, putting a minus in front of it is flipping the ordering. So if this was negative before, it will be positive afterwards. So this is clear. Then the absolute value of a number is 0 if and only if the number itself is 0. This is also easy to see, just by definition of these properties here. I mean, this will be positive if you have something negative, and if the number is not 0 before, it will be, if it's bigger than 0, strictly bigger than 0 before, it will be after, so nothing can happen. So this is also easy to see. Then two more interesting properties. The value of a product, x times y, is the product of the absolute values. And finally, something very important called the triangle inequality. Where this name comes from, I will tell you in a few lectures because there's a geometric interpretation. Namely, so we have seen the absolute value of a product is the same as the product of the values. For the absolute value of a sum, it's not that simple, but we know that this is smaller than or equal to the sum of the two absolute values. Okay. So let's do a formal proof of this thing. A. So if x is non-negative, then it's clear, because then the number stays the same. If x is smaller than 0, then minus x is bigger than 0, as I just said. This is part of the theorem I didn't sketch completely, I didn't mention completely. This is by theorem 138.d. Yes, so if this is positive, and we know that the absolute value has this is precisely this number, so it follows in particular that this is bigger than or equal to 0. B. So we need to show that this holds if and only if the other thing holds. So these two are equivalent. So we want to show both directions separately. So what we first do is we take this and prove that then if the number is 0, then the absolute value is 0. And then we do the other way around. So this is now looking quite stupid, but you need to check this once. If we take, so we need to determine the absolute value of the number 0. And we know that 0 is particularly bigger than or equal to 0. So this means, just by definition of the absolute value, that the absolute value of 0 is the number itself, so 0. Okay, this shows the one direction. Now we take the other one. We assume that the absolute value of a number is 0 and want to derive that x itself must then already be 0. So if the absolute value of x is 0, then by definition of the absolute value, we know that if x was negative, then, as we just mentioned in part A, then the value would be strictly positive. So if the value is 0, then we immediately derive that x is bigger than or equal to 0. But then we know that the value leaves the number unchanged, absolute value leaves the number unchanged. So we know that x is already equal to the absolute value of x equal to 0. So x already is itself 0. Okay, this proves part B. So for part C, it's a bit tedious. We need to make some case distinctions. So we need to, so again, here's part C. The absolute value of the product is the product of the absolute values. And we did distinguish several cases. First of all, first simple case, if x is 0 or y is 0. If one of the two holds, then we know from the theorem that had number 132 before, that the product, if one of the factors is 0, the product is 0. So which corresponds that, since here one of the factors, so then this is 0 here, so on the left-hand side we would get 0, and here we would also get 0 because there would be one factor would be 0, depending on which one, x or y, would be 0. So this follows from theorem 132. Okay, second thing, if both numbers are positive, then there's nothing to show. If x is positive and y is positive, then it's obvious, because the absolute value doesn't change anything. So we would just have x, y on both sides here. So then this doesn't matter. So now for the more interesting cases where there are some negative signs involved. So if x is positive and y is negative, so we would have this combination. Then the previous theorem about orderings would show that the product x times y is again negative. So this is by theorem 138.part E. Hence, we know what the absolute value is, since the number is negative. So the absolute value of x times y would be minus x times y. But there we had a theorem. This is the one that I left as an exercise, or you can use this then and the commutativity of the multiplication, theorem 133.b, to show that this is the same as x times minus y. But if x is positive and y is negative, this is the same as the absolute value of x times the absolute value of y. Done. So this was the one case where this is negative, and the other case where x is negative and y is positive works precisely the same way, analogously. Okay, finally, there's one case missing, namely when both are negative. When x is negative and y is negative. Okay, then again by this theorem about properties of ordered fields, by theorem 138e, it follows that the product x times y is positive. Negative times negative gives positive. Okay, this means that the absolute value of x times y would just be x times y itself. But this was part of, this was, here I've made a mistake, this was part A and not part B. Part B is coming now because theorem 133b said that this is the same as minus x times minus y. And since x and y are negative, these are the absolute values. So this is the same as the absolute value of x times the absolute value of y. And finally we're done, because if you look at the different cases we studied, they cover everything. So yeah, this completes the proof here. Okay, we need to show part D, the triangle inequality. First of all, we make a slight observation, namely by definition of the absolute value. So we know that if it's not negative, nothing changes. If it's negative, it's made positive. This has a simple consequence, namely by definition of the value, it holds for all a in k that a is smaller than or equal to its absolute value. Yeah, very simple, very easy to see. Also, you can see that minus a, which also just flips the sign here, this is also smaller than or equal to the absolute value of a, because nothing much can happen here. So if a is positive, then this will become negative, and since this is non-negative, this will hold anyway. And if this number is negative, this will be precisely equality here. So in both cases this holds, so we know that these things happen. So we know that this always holds. And then we can now use, if we take some elements x and y as in the claim, we can again use the field property, ordered field properties. This time it's 138.c, that the sum x plus y. This x is bounded from above, so this is where we say this, so smaller than or equal to the absolute value of x. This here is smaller than or equal to the absolute value of y, so the addition just gives that this is smaller than or equal to the sum of the absolute values. And if we take this inequality and replace a by x and by y, we get in the same way that minus x plus y, which is the same as minus x minus y, as we observed before, is also smaller than or equal to this. So now we know, since the absolute value of x plus y is one of the two, so this is an element of the set which just contains x plus y and minus x plus y, and both of them are smaller than or equal to this number. So we get that x plus y as the absolute value is smaller than the sum of the two absolute values, and this is what we wanted to show. Okay, so much for that. Now, we've seen that we have already an ordered field, namely the field of rational numbers that I've just briefly defined today. The question is now, why do we need real numbers? Can't we just take the rational numbers and be happy? So do we need anything more? It turns out that there is one problem with Q. Namely, very roughly speaking, it is lacking some numbers. Put this in quotation marks. This is lacking some numbers. In the following sense, we have seen, that was part of this theorem about ordered fields, that x squared is always non-negative for all x in Q. This follows just for general ordered fields. But yeah, some equations here. So, for example, if we take the equation x squared is equal to a for some non-negative number, a might not have a solution. Solution in Q for some non-negative numbers. So, most simple example, oops, sorry, I hope I still, you can still read this. X squared is equal to 2. We know that this would be the square root of 2 that we would like to have a solution. And we know, I won't prove this here, but this has just no solution in Q. There is no such rational number with this property. So this is the problem. If you want to work with these polynomial equations or quadratic equations and so on, we cannot just solve them here in Q. We can solve some, but not all of them. And for technical purposes, this is just where Q is not enough. This is where we want to be able to do more in order to develop a real calculus, as we are planning to in this term. So what we need is an additional axiom. So it turns out these axioms that we have so far are not enough. Q is an ordered field, but there must be an ordered field which behaves better. And it turns out to construct the real numbers, which we will do in the next section, there's just one more property. So there's one additional axiom that we will need to put on the ordered field, and then we will obtain the real numbers. And this will be done in the next section. So see you in the next video.